Hi, my name is Michael, and in this video I want to show you a simulator for logic circuits. We will use this simulator called Circuitverse for building something called an ALU, an arithmetical logical unit, which is an important part of a CPU, a central processing unit. In this video I just want to show you how to use some simple things called logic gates using this simulator. And also want to show you how you can express mathematically the behavior of these logic gates. So this will be just the first video in a sequence of videos for building finally this ALU. The simulator is accessible using a web browser, so we have a web interface, and I will just jump right into this web interface. What you need is some account for this Circuitverse simulator. I already created one. The link is provided in the description and also on the website for this class. So once you created this account, you can jump right into the simulator. And before we go to the mathematical description of the logic gates, let me just show you what we will cover in this video. What you have here on the left is a box with all the circuit elements that are available in the simulator. And what I will show you is from the input devices, this first device, and from the output device, also just the first device. And from the logic gates, which are in here, just the AND gate, the OR gate. I will begin with the NOT gate, and also I will show you the exclusive OR gate. But before we go on with the gates, let me first show you what a logic circuit represents compared to an electrical circuit. If I'm connecting here this input device with the output device, you see the values can be either 0 or 1. And this could be representing in an electrical circuit the following. You could have here a battery which is connected to a switch. The switch can be connected or disconnected, and the states could be represented, for example, with 0 for disconnected and 1 with connected. And this output device could be a lamp, which can be on or off. Off could, for example, mean 0, on could be 1. And that would mean if you now in the electrical circuit measure the voltage between 2 points, it would be significantly different from 0 if the light is on, close to 9 volt if you have a 9 volt battery, and it would be 0 voltage between 2 points if the lamp is off. So that means a logic circuit is just an abstraction for some electrical circuit, which just shows you some significant part, the logic that we're interested in. Okay, about the logic gates, let me just copy this thing here. If you hold the shift key, you can draw a box, then I can copy and paste this, then I disconnect this. Let's arrange this nicely aligned under each other. Now I want to put in between a NOT gate, which is this symbol, so I drag it here. And then I connect the input device with the NOT gate, with this left part of it, which is called the input of the NOT gate. And this here is the output of the NOT gate. This goes to the output device. And then you see the input is negated, inverted. If you have here a 0, you have on the output device a 1, and vice versa. If I have here a 1, I have here a 0. And then you also can think about how could I realize this with electronical parts. In order to describe this later mathematically, let's also give this input and outputs some name, some label. So I just click here on the input device and label it as an X. And this here will get the name NOT X. It's a result of the NOT gate. Then I want to show you next the AND gate. Then I need 2 input devices. The AND gate has 2 inputs. And I need 1 output device to show you the result. And then in between goes this AND gate. So now I'm connecting this with the first input of the AND gate, this with the second input of the AND gate, and the output of the AND gate with the output device. So this here will be called A, this here will be called B, and this gets the label A and B. And then you already can see the logic. If and only if both inputs A and B are 1, the output is 1. That means if I, for example, switch this to 0, the output is 0. And of course, this is easy to be described mathematically. Now I will copy this here again and replace the AND gate with an OR gate. Okay, let's remove this. This here already gets the new name, A or B. Now I connect it again. And now you see, if and only if both inputs are 0, the result is 0, and otherwise it's 1. Okay, so logical OR. And in a similar way, I just will now insert this exclusive OR, this XOR gate. Okay, now this gets the name A XOR B. Okay, if and only if A and B has a different value, the result is 1. That means if both inputs are 0 or both inputs are 1, the result is 0. And if either one of them is 1 and the other one is 0, the result is 1. Also kind of clear. This is what we call an exclusive OR. All the logic gates that I showed you can be described with simple Boolean functions. Now, first of all, what is a Boolean function compared to functions in general? In general, a function is a mapping from a certain domain into a certain codomain. And a Boolean function has a special type of domain and a special type of codomain. And just by the way, another term for codomain would be set of destination. Now, here, this Boolean function f has this domain b exponent n and this codomain b. So the domain and the codomain both are described using this definition for this set b, which has exactly two elements, 0 and 1. And then we know we can interpret differently 0 and 1. For example, 0 could be interpreted as false and 1 as true, or 0 could mean somewhere we are measuring a voltage between 2 points close enough to 0. 1 could mean that we are measuring voltage close enough to 9. Different ways how to interpret this when we relate it to problems in the real world. Now, having here a Cartesian product with an exponent n means that we are describing a gate with n input connectors. For example, the NOT gate had 1 input, so then n would be 1. The other 3 gates, AND, OR, and XOR, had 2 inputs, then n would be 2. In our examples, the output was always scalar valued. We only had 1 output connector. So that's why I'm having here exponent of 1, which I just skipped. But in general, we also could have vector valued Boolean function, then we would also have here a Cartesian product with an exponent larger than 1. We will come back to that in another video, in another application. Now let's go over the gates that we saw and how we can describe them with such functions more formally. Let's say the function f describes a NOT gate. Then we first of all would have the domain B and also the codomain B. And then we also have to specify how a function argument x, for example, gets mapped to the function value f of x. And of course, we can do this, for example, with a formula like that, because x only has possible values either 0 or 1. This formula would do the trick. About the function name, usually it's convenient to use a name which also expresses the meaning of a function. For example, here I want to express that this is a NOT gate. So I could call the function, for example, not instead of f, but I also can use certain symbols that are commonly used and known from other contexts. So for example, I want to use this symbol, the logical not. And I also want to use operator notations for function values, so I don't have to write too many parentheses. Then, of course, I just could use again a formula for describing the function values. But as an alternative, I also can just list the function values depending on their argument. And for Boolean function, this is often convenient. I mean, you need some more writing, but it's sometimes more expressive. So in this case, for example, I can use this table. Here in this first column, I list each and every possible value of the function arguments. We only have 2 rows here because we only have 2 possible values of x. And then in the second column, I show the mapping, the value of the function. So for example, here I would say 0 gets mapped to 1 and 1 gets mapped to 0. And this table and this formula are equivalent to each other. For the function name describing the AND gate, I'm using this symbol for a logical AND. I mean, this makes sense because I can interpret 0 as false and 1 as true. Also note that now the domain is this Cartesian product of b with exponent 2. So that means we have 4 possible inputs. And also note that in this operator notation, I'm not using parentheses. I'm not writing this symbol for the logical AND followed by an open parenthesis followed by a comma b close parenthesis. So I'm just writing it like that. Now for describing the function values, we already saw the mapping. 0, 0 gets mapped to 0, 0, 1 gets mapped to 0, 1, 0 gets mapped to 0, and only 1, 1 gets mapped to 1. Now you also can think, of course, about a formula for computing the function value depending on its argument, and then the formula, for example, would be a times b. That would give you the value of a and b. For the OR gate, I'm using again the symbols from logic, the logical OR. We also have this domain with the exponent 2 in the Cartesian product, and here the mapping you already saw in circuit verse. 0, 0 gets mapped to 0, and any other input gets mapped to 1. And here again, you also could come up with a formula. For example, you could compute the value of the function as a plus b minus a times b. Would do the same trick. And now the last gate that we saw was this exclusive OR. And here I'm using this symbol. That's the logical OR with this dot above it. Another commonly used symbol would be this plus within a circle. And here the mapping you already saw is 0, 0 gets mapped to 0, 0, 1 and 1, 0 gets mapped to 1, and 1, 1 again gets mapped to 0. And here a formula could be a plus b minus 2 times a times b. Would do the same thing. So if the logic circuit just contains one of these logic gates, it's easy to describe it mathematically. More interesting logic circuits, however, will be composed of more than just one logic gate. And then the mathematical description will be a composition of different Boolean functions. And when we are talking about compositions of functions, and in particular compositions of operators, we have to talk about certain conventions that allow us in some cases to omit the parentheses, because then we have a more expressive way to describe things. Think of rules for adding and multiplying numbers, and a rule that multiplication, the operator for multiplication, has a higher precedence compared to the operator for adding numbers. And something similar we will agree on for the logic operators. Now, first of all, look at these expressions on the left and right hand side and convince yourself that you always have the same value left and right of the equal sign. That means in math, you would define an expression like here, where you don't have parentheses at all, as either the left-hand side or the right-hand side. And then it means if you have an expression like that, by definition, it's first of all this here, but because it has the same value as here, you basically can think of having either parenthesis here or here. And then you would say, actually, I don't care about the parenthesis if I just have AND operators. But now think about how you would realize this expression in terms of logic gates. Then you would come up with that. You first have to connect the inputs A and B with an AND gate, and the output of that AND gate would go into a second AND gate. And here, the circuit would look different. You first would connect B and C with an AND gate, and then the output with a second AND gate, which also gets this A input. So that means mathematically both is the same, but the implementation of the expressions would be different. Okay, and similar, you can think about the OR gate, where you also have the freedom to implement it either way, if you only have the same operator within one expression. But then we have also expressions with different operators, and in order to write it down expressive without too many parentheses, we have to deal with some convention for defining the precedence of certain operators. And I will follow some common convention, namely that the NOT operator has the highest precedence, the AND operator has the second highest precedence, then comes the exclusive OR, and the OR operator has the lowest precedence. That means as soon as we agree to this convention, which is the case from now on, it's clear that if I'm writing down an expression like that, I'm meaning this here, where I first have to evaluate the AND operator because it has a higher precedence, and then I evaluate the OR operator. Or I could say, if an expression like that is wanted, I can omit the parenthesis because the AND operator anyway has a higher precedence compared to the OR operator. But of course, this depends on this convention for the operator precedence. Now, let's practice this operator precedence in a more complex example. In this expression, let's first of all read it out loud. This reads as not A and B or A and not B. And if you maybe say it again to yourself, you see this basically means either A or B, or in other words, this is an exclusive OR for A and B. So looking back at the operator precedences, we see we have actually here parentheses around this not A, and we also have parentheses around here, and then also we have parentheses around this part of the expression and also around this part of the expression. But we don't have to write it down, we have them by convention. So that means we have this equality. And then we can do two things. First of all, I show you how you realize this with logic gates and circuit verse. And then secondly, I can show you how you easily can prove mathematically that this expression actually represents an exclusive OR. Here in circuit verse, I already prepared two inputs, A and B, and one output, and this output is supposed to show me the value of this expression. And I'm claiming the expression represents an exclusive OR. So let's prove this by using logic gates. I have to think about the order in which I assemble this expression. If I start with the most inner pair of parentheses, then I will build the circuit from left to right. And you also could start from right to left by looking at what operator is outside of all parentheses, and then you would start with the OR gate. But let's begin with the most inner pair of parentheses, and those contain not A. and the other most inner pair contains a not B. So I will put this not B a little bit more to the right, because now the second most inner pair contains this AND operator with a not A and B and A and not B. So I need two AND gates. The first AND gate goes here, and it gets a not A and it gets a B. Now, here we go. And then a second AND gate, it gets A and not B. And now we are basically done. I just have to connect this result of the first AND gate with the result of the second AND gate. Also note that here some lines are crossing, but we don't have this dot, so it means nothing is connected. Basically one line goes over the other. Okay, but now I can show you that the result, the value of this expression, is actually an exclusive OR. 0, 0 gives 0, 1, 0 gives 1, 0, 1 gives 1, and 1, 1 gives 0. What we did with circuit verse, we also can do with a piece of paper, or we also could say just prove it mathematically. Let me first write down this expression. We had not A and B, or A and not B. And then I will make a table. I need the inputs A and B, and then I will write down all the possible inputs. We only have 4, 0, 0, 0, 1, 1, 0, 1, 1. And now I think about the precedence of operators. So I know that this here needs to be evaluated before I evaluate this. This here needs to be evaluated before I can evaluate this, and then I can evaluate the whole expression. And of course we don't write it down like that. We use instead parentheses, but basically it has the same meaning. So I will use other columns for intermediate results. For example, I need the result of not A later. I also need the result of not B. I need the result of not A and B. I need the result of A and not B. And then I finally can compute the complete expression not A and B, or A and not B. Okay, let's begin with not A. So I just look at the values in this column, and then I just invert them. I negate the values. 0 becomes 1 and 1 becomes 0. So I have here 1, 1, 0, 0. Then I can compute the values in this column. That means I look at the values here, again negate them, and then I have here 1, 0, 1, 0. Done. Okay, next column. I look at the column with not A and the column of B, and then I'm computing not A and B for each row. So that means I have 1 and 0, this is 0. 1 and 1, that's 1. 0 and 0, that's 0. 0 and 1, that's 0. Now let me get rid of that. Then I compute the next column. Now I look at this column and this column. And that means I have 0 and 1, that's 0. 0 and 0, that's 0. 1 and 1, that's 1. 1 and 0, that's 0. And also we are done with that column. And then I can complete this whole thing by looking at the columns here and here. And then I just use an OR operation on this value. So I have here 0 or 0, this is 0. 1 or 0, that's 1. 0 or 1, that's 1, 0 or 0, that's 0. And that means I finally have computed here the values of this expression, and then you see what we have here is exactly A exclusive OR B. So in short, it means we can either go from simple math on some piece of paper where we do some math with Boolean functions and implement our conclusions with logic gates in circuit verse, or we can do it the opposite way. We can build certain logic gates and describe them mathematically and analyze their behavior, and having this freedom to go from one to the other or the way back will be very helpful for our project building an ALU. But for this video, that's enough, I think. Bye.